This question is about specific heat capacity and volume flow rates. So we've sort of got a situation where we've got a heating element within a liquid, and the liquid comes in at one temperature, comes out at a different temperature, and we're giving the change in temperature delta T. Now, I don't like this lowercase t. I've had a few attempts at this question to try and explain it really, really clearly, and I've had difficulty because of this delta t is making my notation difficult. It makes the algebra difficult because delta t is always a time, and I would use capital T for temperatures or theta. But having worked through it, I can sort of see a way of explaining this clearly, so you can understand why each of these answers is right or wrong. And it could be that you can look at the options and you can intuitively decide you've got a feel for it must be that one. You might have a clear idea what it is, but I'll go through it step by step anyway. So Q equals MC delta T is your sort of starting point for this. And then it talks about power, it talks about volume flow rate, talks about specific heat capacity, talks about density. So we need to include all of those values. Now, if I divide both sides by time, so unit time, then the Q changes into call it time rather than lowercase t. And I'm going to use capital T for time, which all feels a bit weird and wrong using lowercase t for temperature and uppercase T for time, but never mind. So I end up with Q over T, which is the power, is MC delta T. Now, M is the volume times the density, C delta T for temperature. Actually, I'll go to their notation. Sorry about that. Over T. Now, V over T is the volume flow rate. It's the volume per unit time, so that's volume flow rate. Now, I can rearrange this for delta T. So delta T is equal to T over V. That means it's inversely proportional to the volume flow rate, because that's the inverse of the volume flow rate. It's proportional to P, the power, which should make sense. And then it's inversely proportional to the density, and it's inversely proportional to the specific heat capacity. Now I have this expression, I can work through and work out which are right and which are wrong. Now, this has taken me probably longer than I want to spend on the question, but I think it's useful to get a good understanding. So increasing the volume flow rate, flow rate. If you run the water through faster, it's not going to spend as long getting hot, so it's going to be cooler. So that's not going to work. Changing the liquid to one of a lower specific heat capacity. If I lower the specific heat capacity, because it's inversely proportional, a lower specific heat capacity means it can hold less energy in joules for a change in temperature. So that will cause a greater heating effect. So that is the right answer. A heating element with a higher resistance. Now, a heating element with a higher resistance, power, if the voltage remains the same, which you'd expect it would because it probably remains voltage, then power is V squared over R. So actually, V stays the same, increase R, well, then the power drops, so that wouldn't help. Change the liquid to one with a higher density. Well, the higher the density of the liquid, the greater the mass flowing through, so the more energy that has to be expended. So that would actually reduce the temperature.